Hashim, and my group members are Michael, Eric, Caleb, and Mahdi, and Abdurrahman. Today we will be talking about our final OBR of the solar panel wings project. An overview of our presentation. First, I will be going over the project goals, including the problem statements and the solution. And then we will go in depth about the electrical and mechanical summary. And at the end, Caleb will walk you through the SDR test that we made and a brief conclusion of our presentation. Our problem statement is to develop a system that will automatically focus more sunlight on a stationary solar panel. And the solution is to build responsive mobile solar powered reflector wings that will increase the power output of a solar panel in an economically efficient manner. Now let's go in depth with the electrical summary. The first thing we're going to talk about the PCB board, including the purpose and creation, benefits and issues we face, and future implementation. And then Michael will go you over operation algorithm, circuit diagram, mobile application, and future steps. The purpose of creating the PCB is to have loose wires and cable management. In order to do this PCB, we used a software called PCB Express software. In order to print this PCB board, we used the laser etcher printer that's provided in the manufacturing lab. And after that, we had to solder this printed circuit board with the breakout pins in order to make the connection between the PCB itself to the electrical components. The electrical components connected to the PCB are the two encoders, the RTC, and the Bluetooth device. The benefits that we get from this PCB is to better wire organization. So we had less wires in the PCB, and also since we label all the breakout pins with the proper naming, so we avoid confusion of the connection between the wires. And the biggest issue that we faced is the sizing of the board. Because the sizing of the board was too small, so we could not include all the electrical components. So we put the Arduino outside of the PCB, and we only include the 4 components that mentioned previously. And this actually results in increasing the wire counts for the PCB. For the future implementation, so we're going to find a better way to include the Arduino, and also we're going to order a larger PCB that will have the capability to include all the electrical components in the PCB design. Now Michael will continue talking about the electrical summary.
So the operational algorithm that we have for our entire project basically follows one of 2 branches. Either the Android application is connected to the Bluetooth module, in which case we would take the right-hand path, or we take the left-hand path that is not connected. When you first turn on the system, you will obviously open the wings to zero out both wing angles and ensure that they are calibrated accordingly. If it is not connected to the Bluetooth module, we will then check the RTC time, and then based on that time, we will find the wing angles. If the wing angles do match, obviously there's no movement, and then we will circle back to the Bluetooth connected conditional statement. If they do not match, when you first turn it on, obviously they're going to be zeroed, and then if there's any change in the wing angle, the motors will actuate in order to match that angle. So if the Bluetooth app is actually connected to the HC05 module, we'll follow the right-hand branch. So we'll basically stay in an infinite while loop while we're waiting for the input stream to fill up with data from the Android application. We can calibrate the wings, we can open the wings, and we can measure the wings. So if you click one of those 3 buttons on the mobile app, it's basically going to implement a function, step back in the while loop. If you do hit the stop wings feature, you will go into a while 1 loop, so basically an infinite while loop, and you cannot do anything until the user presses the resume button. This is if you want to have the system running and operate on it. So if you need maintenance or anything like that and you don't want to completely shut off the system, this is a surefire way to make sure that nothing else happens. If you disconnect from the application, there are 1 of 3 ways to do that. You close out the application, you hit the disconnect button, or you hit the back button. It will obviously go back to the check RTC time and follow the left-hand branch. For the circuit diagram, the main thing to point out here is that we're using an Arduino Uno as the microcontroller. We obviously have the west motor, the east motor, the west encoder, the east encoder, basically parallel for both the east and west motor. While 12-volt battery is basically operating the entire system. The motor driver is basically doing the heavy lifting with the PWM and directional signals. So from the Arduino, the PWM and directional signals are going to the motor driver, and the motor driver is stepping up the voltage and current to actuate the motors appropriately. We do have 2 push buttons which act as calibration for both of the wings. You can see on the left-hand side we have our RTC, and the right-hand side we have the HC05 Bluetooth and slave module. So for the mobile application, what we really wanted to design was something where it was UI friendly. So it was a simplistic UI design with an intuitive UX. So that's why we stayed with the really large buttons, and the nomenclature is presented in a way that makes sure the user understands what they are going to do if they subsequently press a button. So if the user does press a button, just in case they're not entirely sure what's going to happen, we will pop up an alert dialog with the phrase, let's think about that. That happens throughout the entirety of it, and then a short synopsis of what is actually going to happen if you do click yes. If you click no, no action will be taken, and you'll just present it with the screen on the right. So while you have the mobile application up and running, you do have full control of the system. And this actually can be used to troubleshoot the system. So if you accidentally bump into one of the wings, or the belt loosens and flops down, you can calibrate the system rather than having to restart it fully. So rather than having to unplug it and basically replug it in, you can just calibrate the wings and they'll go to the respective angles. Obviously, hindsight is 2020, and with future steps, we would have improved the mobile application. So right now, the measure feature only operates the first time you open up the application. If you hit any subsequent button besides the measure feature and then try to go back, it doesn't work because the input stream is flooded with the other data. So it gives off false readings, basically, of what the voltage and current are from the battery. Also, the set wings angle would be better if you had an input field under the voltage and current for the UI design, and that the user could set the wings appropriately. We would also implement a sleep feature using the RTC. So right now we're not doing too much in terms of power efficiency. So what you would want to do is basically sleep the Arduino for approximately 8 minutes, since the wing angles change every 8 minutes and 15 seconds. After that, you would have to wake up from an alarm from the RTC. A problem with this is if you want to connect the Bluetooth app while it's sleeping, you're going to have another interrupt. So in addition to an interrupt with the RTC alarm, you would also need an interrupt for the Bluetooth module. So that can be implemented easily by a push or something of that sort. Also, as you can see in the right-hand corner, our cable management isn't the best. We did test this outside while it was raining this previous weekend. The solar panel actually sits on top of the H-frame and covers all the electronic components. So nothing got wet and everything stayed secure for about 4 hours while we were running it outside. So even though it looks like a mess, it actually worked appropriately, but we would still like to tie up a lot of the loose ends, just for durability and longevity of the project. Also, we would want to upgrade the motors in terms of efficiency. Right now we have really large motors where it works really, really well, but in terms of efficiency, we're worried that we're actually expelling more energy than we're getting back from the solar panel. So now Eric will talk about the mechanical system.
So first off, I'm going to talk to you guys about the frame. So we went through a pretty significant redesign very early in the semester of the frame. As you can see on the right here, or on the left, excuse me, this is our original design. It's much more complicated. It has some features that we liked, but along with some of our budget concerns that led to us not being able to buy all the material that we wanted to, we had to redesign the frame. So our solution was this H-frame on the right. So the advantages of this frame, first of all, it's much more compact, easier to manufacture. It just has the 4 legs that are much closer together. It also has easier mounting points at each of these ends of the hollow cross member for the bearings that we use to support our wing axles. So one of the problems you might notice with this is that there aren't actually supports any longer for the wings to rest on. This was solved by adding an additional bar to the wing axle that was resting in the bearings, that also gave us a convenient place to put a push button that allowed us to zero out the position of the wing axles. So next, the wings. So one decision that we made early in the project that was really good was our choice of material to use for the wing itself. So these aluminum sheets ended up working very well. They're very reflective and very light, however they're also very flexible. So the challenge was designing a frame that was sturdy enough to support the wing and keep it at the correct angle to reflect light onto the solar panel without hindering the operation of the system. So our initial design was an aluminum frame attached to the back of the wing. We had to scrap this pretty early, again, due to challenges with the costs of the project overall. Our second design that we tried was using PVC to reduce the weight. This was still too heavy, so our final solution, while not terribly elegant, was to attach wood slats on either side of the panel and to use aluminum strip to attach the panel to the forks coming off the wing axle. This ended up working very well. It provided enough rigidity that the wing stayed at a consistent angle with the panel, and it was also light enough that the system was able to operate correctly. So next, our motor, sprocket, and belt system. So this was the most complicated system that we had to design. It took the most work. Fortunately, we were sponsored by Mizumi, and they contributed our sprockets and belt, and that went a long way towards making this easier. But we did still have a few challenges to overcome. First of all, the sprocket we used, the smaller sprocket attached to the motor axle, had too small of a hole to go on the motor axle. So our solution for this was to drill it out to just smaller, a size just smaller than the motor axle itself, heat it up, slide it on, and let it cool, also known as heat fitting or sweating on the sprocket. This worked perfectly for us. So next, the sprocket used to attach to the wing axle was the correct size, but we still had to find a way to make it stay at a consistent angle with the axle. For that, we added a set screw and then machined down the end of the axle to D-shape so that the set screw could find a purchase. So the challenge that we still faced after this, though, was how to get the belt tight enough that it would not slip on either of the sprockets. So we had tried a few different options to try and fix this, from adding counterweight on the other side of the wing axle to try and reduce the torque that was being applied. Our final solution was to machine a slot in the top of the plate that we mounted the motor on. This slot allowed us to tighten the screws most of the way, the bolts most of the way, and then very gently and precisely move the motor plate over with something like a large hammer so that we could get the belt as tight as possible. So some of the challenges that we faced, I've already covered a few of these. The wings being too heavy, this was a design flaw that we saw earlier on that we had to work to overcome. Our final solution being those wooden slats. Next, the belt slipping. So this was the problem that we encountered late in our design that looked the most likely to completely derail us. We tried a lot of different solutions, and that combination of changing the design of the motor mount plate and machining those slots so that we could force it over and add as much tension as possible did end up fixing the problem. Next, the wing axle size relative to the sprockets and bearings. Our wing axle was actually significantly smaller than the bearings. So we had to manufacture bushings that sat inside of the bearings in order to provide support for the axle at those points. So finally, some future steps we'd like to take. We'd like to increase the axle diameter, like I just said. The axle was much smaller than our bearings. We didn't realize that we were going to have the ability to use a much larger axle, and looking back, it would have made a lot of things easier with our project, from attaching the forks onto the axle to hold the wings, to sitting it into bearings, seeing less potential issues with the axle flexing at all. It just would have made our project a lot easier. Also, improving the rigidity of the wings. We think the wood is functional, but we'd like to investigate other options to make them even more rigid without adding too much weight. So improving the belt tension or reducing the necessary belt tension, again, either by adding some kind of a tensioner to the belt, using a chain system, something along those lines that gives us more flexibility. So the leg stability, the system is stable, but there are improvements that we could make either by adding feet to the legs or a crossbar on the rear legs to keep them at a consistent angle with each other and make sure that we keep the panel at the correct 17-degree angle. Finally, the weight. We had talked about the weight a little bit earlier. Our project is pretty heavy. The frame does need to be somewhat heavy because those wings could catch a lot of wind and provide a significant force, and we wouldn't want our project flying away, even though it does have wings. So it was good that our project was at least kind of heavy, but we could definitely improve that in the future. So, and finally, ease of assembly. We ran into a lot of challenges that we didn't anticipate. Now, having the knowledge of the areas where we were going to face difficulties, we could plan our project in such a way that we could assemble it in a more easy follow. So next, I'm going to pass it off to Caleb to talk about our SDRDs.
So first I'll be discussing the tests we performed to fulfill the requirements of our SDRD. As you can see up here on the slide, durability testing was a huge thing that would include wind testing, effectiveness against wet and the rain in general, and things like hail that was asked for proof of surviving hail-like conditions from our customer. Additionally to that, we have the accuracy of the RTC and wing angles. That's super important to ensure that the time is kept like to the second throughout the usage of this system, as everything is dependent on the time of day for this to work. Then the wing angles are super important too, to ensure that the maximum amount of irradiance is striking the surface of the panel to increase the power output as much as we can. And in addition to that, we had a test to study the wing motion accuracy analysis, and that was done to ensure that even with the wind and different environmental conditions, that the wings were capable of moving against these other exterior forces and provide the angles that we desired. At the bottom here is a sample of a video, a time lapse during one of our tests that we took outside of Getherston. So as you can see, Michael's there making sure everything's set up right. And you can see the motion of the wing and that passing of cars. This was one of the tests that we did this last weekend in the rain and wet and cold to make sure that everything was working appropriately. So here are our requirements through the test that were proven on a test by test basis. So as you can see, the durability test, it had to survive Valparaiso March to May March to April conditions for at least 4 hours. We proved this by our test through this weekend, and previously we have done other tests outside. Then the programming needs to be able to run continuously and independent of the user. Michael did a very good job of testing that with the robustness of the code over spring break. He ran it for over 12 hours continuously with the RTC, and everything worked just fine. And then the last very important one is that we set the sun hours and the angles for the system to be like what would be needed in Haiti, as that's the intended location for this project to be placed. Then for the accuracy of the RTC and the wing angles, we needed to use the RTC to ensure that the real world time is kept track of and used to properly angle our wings. And then the wing motion analysis is by far the most complex of these tests, and the requirements there within were much more intense than the other ones. And due to that, we had to measure the amount of light that was striking the panel and ensure that everything was befitting of a Haitian setting. So issues that arose while we were doing this testing. As many groups have had before, we definitely had our issues throughout the building process and especially the testing. So our main issue was inability to perform tests or test certain requirements that we had previously set for ourselves. Measuring the amount of light striking a panel and the power efficiency is a very complex thing with all the differences in sun hours and differences in day-to-day testing and with or without the wings, and including that with the power consumption of our system was very intense, so we couldn't really pinpoint exactly how efficient our system was without more testing. And coming down to the near end of the semester, we just kind of ran out of time to fulfill that requirement. In addition to that, as Michael had spoke on earlier with our voltage and current sensors, the input feeds would always just get overloaded after that usage of the prototype. So it was very hard to have accurate readings of the voltage and the current, and it just made it very hard to keep accurate readings that we could look back on and measure the efficiency. In addition to that, we just ran out of pins on our Arduino for additional exterior sensors. Besides that, very important was self-monitoring of dust is a very near impossible thing. We would need a camera or something that was very accurately continuously measuring the weight of the wings to determine whether or not the wings were increasing in weight with the additional dust, or we'd have to have something measuring every single day how much light was being reflected off of it, which would require a bunch of additional sensors. So lessons learned, teamwork is definitely the most important thing to make the dream work for this project. We learned that communication is definitely very key in order to get our things done on time, and over the course of the semester I think we started to measure a lot better, and you know, as things go, there's definitely some hard times, but there are also some good, very fun times in this group. We learned a lot of new skills with 3D printing for the various housings and the encoder wheels, and we learned how to robustly code things to to create a system that can run for 12 to 16 hours at a time is a very intensive thing, especially when it's an embedded system that's not supposed to be touched by external users after you've set it up. And to have that run concurrently every single day for months at a time is very, very intense. Then testing, we definitely learned that you need to have more time for testing, as testing is one of the most important things of a prototype. Proving that something works is more important than just building it. So, and then thoughts for the future, I'd say that lots of us were very interested in renewable energy and would seek to look into this kind of project in the future for sure. In conclusion, we went over project goals, the electrical summary, the mechanical summary, and we looked into our SDRD testing and what we all learned as a group. So, thank you. Are there any questions?
So, for the aluminum, I know you had done this before, but and you had presented it before, but you got a certain reflection coefficient that was above 90 or something when it's clean, right? But then you also have a profile like the spectrum. So how does it reflect for given wavelengths? And so, can you give me an idea of how flat that is and visible?
Sure. So, sorry, I'll take this one. So the question is, how does the reflectivity of the aluminum panel correspond to visible light wavelengths and will be used by the solar panel? So yeah, I had addressed this in an earlier OPR. I don't have the chart in here anymore, but the aluminum actually has a very high, that particular reflectivity of over 0.9, especially for the visible light wavelengths. So that's about 0.4 to 0.7 micrometers. So these are the wavelengths that are actually used by the solar panel in particular. So it is very consistently high for those relevant wavelengths to be used by a photovoltaic cell. And so that was the most important area for reflection, and that was where it was.
So that was going to be my follow-up. What's the receptivity of the solar panel? You said between 400 and 700 nanometers?
That's correct. That's where the PV cells are designed to take advantage of the light wavelengths.
So let's say you had a few more months. Can you give us an idea of how you would test efficiency?
I think the first step would be ensuring that our sensors were definitely operating correctly. That would probably need to be done by changing which Arduino we are using to have one with more input pins, so we can have external sensors on instead of just reading from the ADC on the actual board. That would increase the amount of accuracy we have with those readings, and we would have a more diverse selection of sensors that we could use instead of using a couple resistors to measure current and like oscilloscopes match to that and things like that. So I think that what we would do over a couple months period would definitely be many tests running through different conditions, whether it be cloudy outside or a bright sunny day. Solar panels actually have a max capacity of a radius that can strike a panel, and we are unsure if we would actually hit that up like the top level with our wings in addition to just a bright sunny summer day. So seeing if we could hit that cap would be definitely a huge goal for this, and seeing if the light during a cloudy day would be more beneficial than on a sunny day off of our wings. Does that answer your question?
With the wings, when you showed it with the video, so it was just going off of time then? You had to tell it what time it was and what date it was, and then it went to a specific angle?
So the question was, how were the wings angling themselves appropriately? So with the way that we were setting that test up, we actually had predetermined a accelerated pace to meet that 4-hour goal. So it wasn't like a full day length. It matched the angles appropriate of what it would need to be at that day and that time of day in Haiti. So it was actually angling through all those positions at a rapid pace.
But when you set it up, you got to know where it's pointing north, or you got to get it set up with the compass. Like if you deploy it, and then you'd have to have a leveling procedure as well.
So the question is, so as far as leveling goes, so solar panels actually So there are a couple different ways you can set it up. Like the group in the morning section, you can actually change the angle over the course of the year, or there's also a best angle at each individual latitude of the Earth. So for Haiti, that's 17%, and that's what we had our frame set up to provide for the solar panel for a constant year-round. It would have to be aligned correctly north-south, but beyond that, as long as it's set up correctly and angled north-south, everything else will be taken care of by the angles that we've programmed for the wings to take.
Yeah, so there's a lot of geometry to think about there, right?
There's-
So you get it set up right, as long as you get it set up right, but then you can increase and decrease in Haiti, and it's not going to be as much throughout the year. But then you have to know the time of day, but you're also taking into account the day of the year as well, right?
So the question is, sorry, it's hard to like. Okay, all right. Yeah. So what we did with our program and the way that we set up this program, we set it so it'd be at that angle that Eric was speaking about to be the best setup and stationary angle for a solar panel to reach the max amount of radiance, right? And then what we did with the wings is we looked at sun hour charts in Haiti exactly, and like you said, it actually doesn't deviate very much from day to day, month to month. It's essentially like a very slight sinusoid. And so what we did is we set it up for the best estimation of those angles. If we were setting the system up for a place in North America, or Valparaiso particularly, the sun hour chart goes more like this, and a huge steep drop off twice through the year, winter especially, and so that we would have to take exactly every single day into account. In a future implementation of the system, we would go day by day in Haiti too, just to get that max peak power output. But for now, it was actually best and more efficient coding to just angle the wings to just reflect it at the average estimated best angles throughout a day.
So yeah, to go more off of that, it's basically a bucket of time, and then a specific wing angle associated with that time interval. So it starts around 5:50 in the morning, and then adjusts accordingly until 11:30. At 11:30 it drops down, just because it's basically going to be overhead, and it stays there all the way until 12:30. 12:30 we start actuating in the east motor, and then we basically drop it down to 6 p.m. and then we don't do anything from like 6 to 6 essentially.
Any more questions? Thanks for your time.